Picture a tiny spacecraft, smaller than a car, racing through the darkness of space. It's been traveling for decades, leaving Earth, a pale blue dot, and even the sun behind. This real-life explorer is on a mission to leave the solar system and enter the unknown between the stars. We've sent robotic ambassadors on this journey, pushing the limits of science and engineering. Their mission to answer our biggest questions. What's out there? Are we alone? What lies beyond the sun's reach? Escaping the solar system isn't easy. It takes immense speed, careful planning, and a little help from the planets. Think of it as throwing a ball so hard it never comes back, except the ball is a complex machine and you're escaping a star's gravity. Every bit of data these pioneers send back adds to our understanding of the universe. So, how do you build a spacecraft that can say goodbye to the sun? It all starts with one key idea: escape velocity. Escape velocity sounds complex, but it's simple. It's the speed you need to break free from a planet's gravity. Throw a ball up, it falls back. Throw it fast enough, and it escapes forever. Every planet and star has its own escape velocity, based on its mass. To leave Earth, a rocket must hit about 11.2 kilometers per second, nearly 25,000 miles per hour. But escaping Earth is just the first step. The sun's gravity is far stronger, holding the entire solar system in its grip. Even after leaving Earth, a spacecraft still orbits the sun. To truly leave, it must escape the sun's gravity, a much bigger challenge. Imagine Russian nesting dolls. First you escape Earth, then you face the sun's much larger doll. Escaping the sun is the final step to becoming an interstellar traveler. It's the ultimate speed limit for leaving our cosmic home. The sun is the solar system's gravity king, reigning at the very heart of our cosmic neighborhood. Its presence is not just about light and heat. It's about power, control, and the invisible force that shapes everything around it. The sun holds over 99.8% of the solar system's total mass, making it by far the most dominant object in our corner of the galaxy. Imagine all the planets, moons, asteroids, and comets combined. They're just a tiny fraction compared to the sun's immense bulk. Its gravity acts like a cosmic anchor, keeping planets, moons, and comets locked in their orbits. Without the sun's pull, the solar system would simply fly apart, with planets drifting off into the void. When a spacecraft escapes Earth's gravity, it doesn't just float freely. It immediately falls under the sun's influence, becoming a tiny, artificial planet in its own right, endlessly circling our star. To truly break free, a spacecraft must overcome the sun's immense gravitational pull, which is far stronger than anything we experience on Earth. Picture the sun's gravity as a giant whirlpool in space. The closer you get, the more energy you need to escape its swirling grasp. It's a relentless force, always pulling you back. The sun's gravity well doesn't just stop at Pluto. It stretches far beyond, reaching out to the distant Oort cloud, a shell of icy objects nearly a light year away. Even billions of miles from the sun, its gravitational tug is still felt. Spacecraft venturing into the outer reaches of the solar system remain under its influence for decades. That's why a simple rocket launch isn't enough to escape the solar system. The sun's grip is just too strong for ordinary engines to break free. Once the engines shut off, the spacecraft is left to coast, locked in a delicate balance, always fighting the sun's pull as it travels through space. The real challenge is finding enough energy to climb out of this deep gravity well. It takes careful planning, powerful rockets, and sometimes even gravity assists from other planets. Escaping the sun's grasp isn't just about pointing a rocket and firing. It's a cosmic game of physics, where every move must be calculated with precision. Only by understanding and using the rules of the solar system, gravity, momentum, and orbital mechanics, can we set a course for true interstellar space, leaving the sun's kingdom behind. To escape the sun's gravity, a spacecraft must reach solar escape velocity. This speed depends on distance from the sun. The closer you are, the faster you must go. From Earth's orbit, the magic number is about 42.1 kilometers per second, roughly 94,000 miles per hour. Any slower, and the spacecraft stays trapped in orbit. Luckily, Earth is already moving at nearly 30 kilometers per second around the sun. By launching in the same direction as Earth's motion, we get a huge head start. The rocket only needs to provide the extra push to reach escape speed. Even with this boost, reaching solar escape velocity is a monumental task. Achieving these speeds requires the most powerful rockets and clever tricks. Hitting that 42.1 kilometers per second is the key to unlocking interstellar space. So, how do we actually reach those incredible speeds? The first step is a powerful rocket launch, but that's rarely enough to escape the sun. Rocket fuel is heavy and limited. Once it's gone, the engines stop. That's where gravity assists come in. A spacecraft flies close to a massive planet like Jupiter and uses its gravity to slingshot itself faster. It's like grabbing onto a fast-moving truck while on a skateboard. The planet's gravity gives a free speed boost. No extra fuel needed, just clever navigation. All our interstellar missions use this trick, combining rocket launches with gravity assists to build up speed. Each planetary flyby adds more velocity, pushing the spacecraft closer to escape. It's a cosmic game of billiards, using planets as stepping stones to the stars. The Voyagers are the best examples of escaping the solar system. Launched in 1977, Voyager 1 and 2 used gravity assists from Jupiter and Saturn to gain speed. Voyager 1's slingshot at Jupiter and Saturn put it on a path out of the solar system. It's now the fastest, most distant human-made object. Voyager 2 visited all 4 giant planets, using each as a stepping stone to build up escape velocity. New Horizons, launched in 2006, was the fastest launch ever, but still needed a Jupiter flyby for a massive speed boost. That slingshot saved years of travel time and sent it racing toward Pluto. After its Pluto flyby, New Horizons was on an escape path, never to return to the inner solar system. These missions proved we can use the planets themselves to reach interstellar space. They're our pioneers, showing what's possible with clever engineering and cosmic strategy. Their journeys paved the way for future exploration. Where exactly is the edge of the solar system? It's a question that has fascinated astronomers and dreamers alike for generations. Is it where the last planet orbits? Or is there something more mysterious marking the true boundary? The answer lies at a place called the heliopause, the invisible frontier where the sun's solar wind finally meets the vastness of interstellar space, far beyond the orbit of Pluto. The sun constantly blows a bubble of charged particles known as the heliosphere. This immense bubble acts as a protective shield, enveloping all the planets and most objects in our solar system, and shielding them from the harsh cosmic radiation that fills the galaxy. But as you travel farther from the sun, the solar wind grows weaker until it finally collides with the interstellar medium, the thin gas and dust that fills the space between stars. The heliopause marks the place where the sun's influence ends and true interstellar space begins. It's the ultimate border, separating our solar neighborhood from the rest of the galaxy. In 2012, Voyager 1 became the first human-made object to cross this boundary, venturing into interstellar space after a journey of more than 3 decades. Its instruments recorded a dramatic drop in solar particles and a sudden spike in cosmic rays, clear evidence that it had left the sun's protective bubble and entered a new realm. Voyager 2 followed in 2018, confirming Voyager 1's findings and providing even more data about this mysterious, unexplored region at the edge of our solar system. Yet, even beyond the heliopause, the sun's gravity still stretches outward, reaching all the way to the distant Oort cloud, a vast shell of icy objects that marks the true outer limits of the sun's domain. It will take tens of thousands of years for the Voyager spacecraft to travel beyond the Oort cloud and finally escape the sun's gravitational grip entirely. But crossing the heliopause is a monumental first step, a leap into the vast, uncharted unknown that lies between the stars. These milestones are not just technical achievements, they mark humanity's first entry into the space between the stars, a testament to our curiosity and desire to explore. The journey continues as our spacecraft travel farther than ever before, carrying our hopes and questions into the endless depths of interstellar space. Reaching the stars isn't just about speed, it's about surviving the journey. The distances are staggering. Even at tens of thousands of miles per hour, it takes decades to reach the edge of the solar system. Spacecraft must be incredibly reliable, enduring extreme cold radiation and the vacuum of space for decades. Far from the sun, solar panels are useless, so missions like Voyager use radioisotope thermoelectric generators, RTGs, for power. RTGs convert heat from radioactive decay into electricity, providing steady power for decades. Communication is another challenge. Signals from Voyager are billions of times weaker than a watch battery and take nearly a day to reach Earth. Giant radio antennas, like the Deep Space Network, are needed to catch these faint whispers. Long missions require patience and dedication. Teams must manage dwindling power and aging instruments. Every bit of data from interstellar space is precious and hard-won. The challenges make each discovery even more remarkable. Our current spacecraft are fast by human standards, but when you look at the vast distances between stars, they're actually incredibly slow, almost crawling across the cosmic ocean. For example, Voyager 1, the farthest human-made object from Earth, would take an astonishing 70,000 years just to reach the nearest star beyond our Sun. If we want to explore other star systems within a single human lifetime, we'll need to invent and build entirely new kinds of spacecraft, using technology that's only now becoming possible. One promising breakthrough is ion propulsion. This system uses electricity to accelerate charged particles, or ions, out the back of the engine at high speed, providing a gentle but steady push that, over months and years, allows a spacecraft to reach much higher speeds than traditional rockets. NASA's Dawn and Deep Space One missions have already shown that ion drives can work in the real world, traveling to asteroids and comets far from Earth. Another futuristic idea is the solar sail. Imagine a giant mirror-like sheet that unfolds in space and is pushed forward by the pressure of sunlight itself. Each photon of light delivers a tiny nudge, but over time these nudges add up, giving the spacecraft a continuous, fuel-free push. This allows the spacecraft to sail across the void, riding on beams of starlight to destinations far beyond our solar system. The most ambitious concept yet is Breakthrough Starshot, a plan to send swarms of tiny, lightweight probes equipped with solar sails and accelerate them to incredible speeds using powerful lasers fired from Earth's surface. These miniature spacecraft could reach up to 20% the speed of light, fast enough to cross the distance to Proxima Centauri, our nearest neighboring star, in just over 20 years. That means we could send robotic explorers to another star system within a single generation. While these technologies are still in the experimental stage, scientists and engineers are making rapid progress, testing new materials and propulsion methods in labs around the world. Each new idea brings us closer to the dream of interstellar travel, showing just how determined we are to push the boundaries of exploration. Escaping the solar system is only the first step. The real adventure lies beyond, in the vast unknown between the stars. Our ultimate goal is to reach the stars themselves, to explore new worlds and perhaps one day find life beyond Earth. The next chapter of space exploration is just beginning, and the possibilities are as limitless as the universe itself.